Welcome to the third session of our course on durability of concrete structures. Today, last two sessions we covered part 1 on corrosion of steel reinforcements, and in the part 2 we covered deterioration of concrete. Today we will be focusing more on durability based design and what are the type of things which we have to do on site so that we can actually achieve durable structures or build durable structures. So, let us go into the durability based design. What I will be covering is giving you a background and then how to enhance durability of concrete structures. Basically, we will be looking at use of mineral and chemical admixtures and also at the placing and curing of concrete at site. And then we will also go through some test which can be done to check whether the structure will actually achieve its desired durability or not, or rather to look at the properties of the concrete. And then we will also go through some provisions given in the Indian and other codes on durability. Then we will give you a brief on software for predicting the service life. And we will also tell a little bit about what is the preventive maintenance required. So, background. So, we in general think that concrete will take care of everything by itself. So, we have an expected performance which is given on the left side of the slide, and what we actually see is on the right side of the slide when especially when we do not really do a quality construction. These are the things something which we can see. So, as an expected performance, we think that concrete is inherently a durable material. However, we have seen premature deterioration of many concrete structures built today or very recently, and we also think that the concrete structures can be maintenance free during their service life. But what we have seen is there is a huge cost of corrosion and repair, etc., which can be even up to about 50% of the construction budgets. So, it is not really maintenance free, and to be precisely we must actually maintain this concrete structure or monitor and maintain the concrete structure, so that the cost of corrosion or repair is going to be minimal. And we spend about 3 to 5% of our GDP for maintaining or to repair, to take care of the corrosion, etc., on our concrete infrastructure. And also we think that most of the research findings are directly getting implemented in industry. That is what we expect to happen. However, we see that there is a really some lag behind, even though we know some things are not really good, but due to lack of good workmanship and other reasons, we are sometimes not able to actually implement what we find through our research, and there is a significant lag sometimes. But eventually, that is our goal of this course, is eventually we should be able to implement whatever we know and how to actually build long lasting structures. So, the following conventional wisdom may be sometimes incorrect. I am not saying always it is incorrect, but sometimes it can be incorrect. And what we think is durability and other engineering properties of concrete are a function of FCK. For example, if you actually talk to an engineer at site, they will talk about one parameter of concrete, that is the strength or characteristic strength or FCK of the concrete. We do not normally talk about what is the permeability and chloride resistance, carbonation resistance, etc., of the concrete. When most cases we do not look at all these other parameters, we look at only the strength, and then we have an assumption that if strength is better, then everything else is going to be good, which may not be true all the time. If cube strength are okay, then the concrete in the structure is fine. So, this again second bullet may not be true all the time, it may have some other, we may have to look at other properties as well. And also we think that concrete is very forgiving, whatever we do it will take care of itself. I think we have this feeling, and that is why we mostly have unskilled labor at site. We allow unskilled labor to do concreting at site, whereas when you look at other industries where definitely, like for example, if you are talking about industry, automotive industry or any other industry for that matter, they want people to have some certain skills and certified, so that then only they will actually hire them. But in our construction industry, we have a lot of many of our workmen, they are actually sometimes uneducated or unskilled, and then we cannot really expect them to know everything about cement and concrete and ensure good practices at site. So we have to really there is a long way to go, especially when we consider Indian construction industry. We have to really train our workforce about many scientific aspects, or how to do good things, or train them on good construction practices, good concreting practices, etc. Now, when we talk about durability, durability depends on both the concrete and the environment. It's not only that, it's not that all the concrete will work very good in all the environment. For example, if you talk about the concrete system, there are material aspects, like which type of material is being used, binder, what type of the binder or what type of cement is being used, what type of fly ash, what type of slag, etc. And then aggregates, and then admixtures and how they are proportioned. And if you are talking about the process of concrete making, how we mix the concrete, how we transport, compact, curing, temperature, workmanship, all these are actually very crucial when we talk about deciding on the durability of concrete. And also at the same time, here on the left side we are talking more about the concrete by itself. On the right side we are also talking about the what can actually go wrong, or how the concrete can get affected because of the aggressiveness of the environment. For example, if you have a very dry environment and if you don't have proper curing conditions prevailing at the site, then you can have significant shrinkage experiencing on the concrete can experience significant shrinkage. Again, if the load conditions are too much than what is actually designed for, then you can have creep, abrasion, erosion. All these are all dependent, basically dependent on the environmental conditions and load conditions. And we also have some chemical actions, which is dissolution and then leaching of materials from within the concrete. Concrete can also undergo expansion due to various chemical reactions like ASR, etc., which can lead to cracking of concrete. And also due to the prolonged chemical reaction, you can actually have changes in the phases of various hydrates in the concrete. Anyway, the point is we have severe issues associated with the specification on the concrete. For the concrete, how do we specify that my concrete should have or how do we specify the concrete? Normally we go for something called performance specifications. That has been the practice in the past, but now the world is moving towards using prescriptive specifications, which is given on the right side. For example, on the performance based specification, I'm sorry, actually the one which is given on the left side, there is a one which is given on the left side is performance based specification, one which is given on the right side is the prescriptive based specifications. We have been in the past, we have been going for prescriptive specifications where curing duration and what method to cure, what is the minimum cement content, what is the type of binder to be used, what is the amount of water and cement to be used, etc. Whereas these are like prescription, you only tell the worker or the people at site how to do things or what to do, not on what to achieve. For example, if you look at this side, on the left side, we have performance specifications where we say, okay, whatever you do, your compressive strength or tensile strength of the concrete should be so and so at a particular time. For example, cover depth, if you have a deck being cast, we can actually check whether the cover depth is appropriate or not, because most of the time we see that the cover depth is actually much less than the prescribed cover depth. So here what we can say is performance. You put this cover depth as a, and then after the construction is over, there are now technology available to actually measure what is the cover depth without even opening at the concrete. You can do some non-destructive testing and then find what is the cover depth. And then we can also specify something on shrinkage. We can say after about a month or 28 days, or even after some time, a couple of months, we can say that concrete should not have this much shrinkage, otherwise you will have shrinkage related issues. And then we can also specify on the permeability characteristics of concrete. For example, chloride permeability, water permeability, oxygen permeability, carbon dioxide, how fast the rate of carbonation, various things we can specify. The point to be noted is on the left side, what you see is something which we measure on the concrete. On the right side, what you have is the prescription, like a doctor's prescription. We tell what to do. And the problem here is, if you tell what to do, as you see on the right side, there is no way to check what's its impact, whether even at the site, if they don't do a good job, there is no way to check on that. So that is why it is important to go for the specifications as it is given on the left side, where we give the full responsibility to the builder or the contractor who is doing the job, and giving them the responsibility of achieving these properties after a particular time period. So they will be careful in achieving these properties. So that we are basically saying it's the performance of the concrete, not what is there inside the concrete we are worried about, but it is how the concrete performs. That's what we are worried about. So world is moving towards using the performance based specifications, and that's a way which we should also go. Now, what is needed to enhance the service life, or what is needed to enhance the performance of our structures? One objective is to enhance the quality of the cover concrete against the ingress of various deleterious elements. And approach 2 is to enhance the quality of the steel which is embedded inside the concrete. So we need a balanced approach. It's not that use the best quality concrete and then not use a good quality steel, or the vice versa. We have to actually have both concrete and steel should be of good quality, so that we can achieve optimal performance of the structures. So to this actually what this module will focus more on the concrete cover part. So as you see here in this structure, you have a reinforcement which is here, and then you have cover concrete. So this is how a structure, like if you have a concrete column, how it will look like is something like this, where both the concrete and steel needs to be protected from the external elements. So what this is a schematic of the column which is like this. So you can see on the left side you have a concrete which is having a porous cover concrete or poor quality cover concrete, and inside the stirrup you have good quality concrete, or the hardcrete is very good, but the covercrete is of poor quality. So what will happen, these deleterious agents like chloride, moisture, oxygen, carbon dioxide, etc., sulfates, all that, they can penetrate through the cover concrete and reach the steel reinforcement, which eventually will lead to either cracking and corrosion and then cracking. What we need is, we have to ensure that the covercrete also is of very good quality like the hardcrete. Then these deleterious agents will find it very difficult to penetrate through this concrete and reach the steel. So this is the whole concept of how to enhance the concrete durability. Idea is to ensure that the cover concrete is also equally good as the hardcrete. So the corecrete will give you a good strength, but if you are talking about durability, you have to focus on how good the covercrete is going to be, not only the corecrete. So why this happens like this case in the left side is because we don't normally cure the concrete properly. So curing becomes very essential to ensure you have a durable structure. So the takeaway from this slide is covercrete with low permeability is essential to achieve durability. Low permeability means it should be resistant against chloride, oxygen, moisture, carbon dioxide, etc., sulfates, etc. Now, how do we do that? So let's look at how to enhance the durability of structures. What are the ways to do? When we talk about fresh and hardened properties of concrete, we will look at both fresh and hardened properties. So what you see, this picture here shows, we can actually, there are different types of mineral admixtures available: fly ash, slag, silica fume, metakaolin, and many other rice husk ash. So different materials are available, or mineral admixtures are available, which can be actually incorporated into the concrete so that you can enhance the properties. And this mineral admixtures mainly enhances the hardened properties, and chemical admixtures we can use to enhance the fresh properties, like superplasticizers are widely used to enhance the flow properties of the concrete, but there are also other chemicals which are very specific and can be used to enhance later age properties as well. We will not go into much details about all that. And there is one more concept is get a very good particle packing of the materials which are used. For example, if you put these mineral admixtures in concrete, you can actually look at the size of the particle size distribution of various materials which are going into the ingredients of the concrete, including fine aggregate and the cement and all the mineral admixtures and any other fine filler, everything we put together and get the particle size distribution of all these materials, and then we finalize on what proportion of each material, what should be the proportion, so that you can get best particle packing, or the maximum compaction, compaction with minimum voids can be achieved. And also another thing I would like to mention here is we should use cement as a binder but not as a filler. When we have a tendency normally, when you want to increase the strength of the concrete, first time people think is just to put more cement, it will give you more strength. It should not be considered like that, because it's not just adding cement, it's actually how better packing we get. And one more thing is, if you put too much of cement, then it is actually not good for concrete, because cement will generate more heat, it will lead to some thermal cracking, and which can eventually affect the concrete's durability. So idea should not be use cement as a filler, but cement should be used or as a binder, just to keep all the coarse and fine aggregates together. That should be the idea. Now when we say durability, these are the three things which we have to worry about when we may do a mixed design. One is workability, means looking at basically the fresh properties of the concrete, and then strength, and then durability. Now what is durability? It's nothing but ensuring strength for long term, or performance for longer term. Not only at the time of construction, we should ensure that the structure will be able to take the loads even after several decades and after the construction. So durability essentially means strength for long term. Now how to enhance the fresh properties? So we have to worry about workability. How we do that is by using one of the way of enhancing fresh properties by using chemical admixtures. And one of the chemical admixture which is widely used for achieving this flow property, good flow, is superplasticizer. As you see on this left picture, what you see is a concrete which is having a low water cement ratio, but having no superplasticizer. So what you see here is there is an agglomeration happening, or the cement particles are coming together and it traps some water in between those cement particles. So, this water is not available for ensuring good flow. So, there is an entrapped water, and when you put super plasticizer, what we can see is all these cement particles, like these 5 cement particles here, they are now well separated. On the left side, you see they are all clubbed together or agglomerated. Now here they are not coming together, or there is no agglomeration. In each cement particle is kept separated, and you have water, or even this water is available for the chemical reaction and for ensuring good flow. So in fact, we are able to achieve better flow with low water content if you are using super plasticizer. Now, this is how the mechanism or how we are able to keep these cement particles separated. We will show that how that mechanism is in the next slide. Now, formation of adsorbed layer on the cement particles. When we put the super plasticizers, what happens is they actually go and get adsorbed on the surface of the cement particles, and you have a negative charge all around the cement particle. Now, every cement grain will have this negative charge around. So, what here, if you look at this point here, you will have these negative, 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 and then all these negative charge, they will not be able to come together. There will be a repulsive force. So, that is what we call electrostatic repulsion. So, because of this electrostatic repulsion, we are able to prevent the flocculation of the cement particles. Also, there is one more mechanism which is called steric hindrance. It is like this small fiber like molecules, they will actually get adsorbed to the cement surface, and it will be very difficult for this cement particle to come closer to this cement particle because of these molecules. They will try to prevent. So, it is similar to when you have the brush, if you like bristles on this toothbrush. So, you can't really reach this point on this brush because of this bristle. So, similar way you can think of, it's just an analogy to explain things. So, this because of the steric hindrance, you will not have these cement particles coming closer. Now, consequences of super plasticizer uses: reduces placing and compaction time, leading to lower construction cost. Because now your concrete is easily workable, it is easy to place the concrete and easy to compact the concrete. It takes less time, and it basically lower the construction cost. Like in construction, time is money. So, less the time, cost is going to be less. Now, it also facilitates the casting of the elements with complex shapes and dense reinforcement, because when you have complex shape and dense reinforcement, especially if you have dense reinforcement, if the flow or workability of the concrete is not good, then it will be very difficult to make the concrete flow through the rebar and then fill all the spaces in the formwork. So, you have, by ensuring the workability or enhancing the workability, you are actually able to place concrete even through dense reinforcement. Of course, you have to consider the aggregate size, maximum size of the aggregates, but we are talking about mainly the aspects associated with the cement paste. Now, also it improves the surface finish of the concrete elements. The concrete will look smooth finish you will be able to achieve, and then it leads to superior strength and durability with low cement content. Especially when we put super plasticizer, we are able to achieve concrete with similar properties or better properties with lower water content without actually influencing the workability. Let me explain this once more. As you see on these two pictures, on the top photograph, top picture, you can see the water cement ratio is 0.65, means you have a lot of water. This white region here is, or light gray region here is water, and you have less cement. So, water cement ratio here is higher as compared to the water cement ratio in the lower picture, which is only 0.25 or something, just to give you a sense of what we are talking. Now, by looking at it, you can say this concrete, if you have this cement paste, is going to flow much easier as compared to this cement paste. But if we put super plasticizer here in the second case, we can achieve very similar workability or good flow like this concrete on the top. So, the idea is use less cement and use super plasticizer, so that you do not compromise on the workability or flow properties. So, you can get good quality concrete at the end. So, nutshell is lower the water cement ratio, use the super plasticizer to get the workability or fresh properties, better fresh properties. Now, let us look at the properties of the hardened concrete. So, features, we said that we can use mineral admixtures to enhance the property of the hardened concrete. So, features of SCMs, one is rich in silica, or SCM stands for supplementary cementitious materials. In India, we also call it as mineral admixtures. The word mineral admixtures, when it's mostly used in the Indian subcontinent. When you go out or in the journal papers, you will mostly see the term called supplementary cementitious materials. How do we decide a material can be used as a supplementary cementitious material? Is by checking whether it has a significant amount of silica or not. So, for example, fly ash, slag, silica fume, metakaolin, they all have significant amount of amorphous silica in it. And also filler effect is sometimes used. For example, if you are talking about, it's not that only the chemical reaction part or pozzolanic reaction part, we can see that there are some material which will be staying inside the concrete and it has a filler effect. Especially when you talk about silica fume, it is very small in size, so it actually helps in filling the fine pores between the cement particles. So, you can see here this picture where you have one cement particle something like this size and where you have silica fume which is much smaller. You can see it is even less than a micron size. One of the, it's a fume, so it's just like the smoke particles, silica fume. But let me make it very clear, we are not saying that silica fume is used only as a filler material. It has both pozzolanic and filler effect. That's what I meant to say. So, any of these materials you can expect to have, depending on the particle size distribution, both pozzolanic reaction and filler effect can be there, but mainly we are focusing on the pozzolanic action. Now, what is pozzolanic action? See this slide, I'm sorry, it got corrupted in this slide. So, the C2S, C3S and water, these are the three basically the reaction in the hydraulic cement, where you can say these C2S and C3S is coming from the cement. So, please ignore this part here, this 1 4 4 4 4 2 4 4 3. So, that can please ignore that part, and H stands for the water, and here you have CH and CSH. So, CH is the calcium hydroxide and CSH is the calcium silicate hydrate. So, this equation is the reaction, hydraulic reaction. Now, as a product of this cement hydraulic reaction, you have CH. Now, what happens is the CH is combined with the silica S here. Again, please ignore this 1 4 2 4 3. It's again a software issue. So, this silica from the SCMs like fly ash, slag, silica fume, metakaolin, etc., that gets it reacts with the CH which is formed in the cement hydration reaction. These two combines together to form more CSH in the same volume. So, you essentially get a more compact microstructure. That is the advantage of using SCM. So, same content, same volume, you can have a more compact microstructure when you use supplementary cementitious materials. Now, concrete becomes stronger and less permeable. More compact means you can have a higher strength and permeability can be low when fly ash, silica, slag, fly ash, slag, silica fume, metakaolin, etc. are added. I should say we should say added. Actually, it's a replacement. When we use SEMs, we actually replace some part of the cement, or partial replacement of cement is what we do. We don't actually add. That's not the right term. We should say it's a replacement. Now, today we use a significant amount of SEMs in most of our concretes. One challenge here in achieving whatever we discussed in the previous slide, in achieving this more compact microstructure, which will lead to higher strength and lower permeability, is to ensure that it is very well cured. For example, if you are talking about an OPC concrete, in the lab conditions, when we test the concrete, we cure it for 28 days. But if you are talking in a field condition, mostly concretes are moisture cured or water cured for about 7 days, and then we see a lot of structures which are not cured after the 7th day. In the PPC system or fly ash or any slag cement systems, we should at least cure it for 14 or 21 days of 21 days. If we do not cure it for this additional time, we will not see the desired strength and other durability properties. So, curing becomes very essential to achieve the desired quality. It is not just using fly ash, slag and other good materials. We should also ensure that the concrete gets properly cured, otherwise it will not be a good concrete. It's like cooking food. When it's not just the ingredients which we use, it's how we make it also. That's why we have different same dish name might be same, but it has different taste. That's because you have better quality in the making of that food. So it's not just the ingredients. Like here also, it's not just putting these SEMs in concrete, but at the same time you have to allow it to cure for longer duration, so that you can actually exploit all the good properties of those materials. Now, how do we cure? Basically, curing means ensuring that enough water is available for the concrete to continue the hydration and pozzolanic reactions. So here you have this, if it is not properly cured, water will be evaporating from the surface of the concrete. So for example, here this is the way we should have ponding. The concrete should be ponded with water. Here there is an example showing that water, and then on top of the water you put a plastic sheet, so that there is no evaporation of that free water. Now, in future we are going to see a significant issue in actually making that enough water is available, ensuring that enough water is available. So, we have to start thinking about water footprint of our concreting processes or concrete structures. So, one way of reducing this demand for curing water is to use something called curing compounds. Is to use curing compounds, and curing compounds, even of curing compounds. So, in this case there is a lack of knowledge on the need for adequate curing to achieve durability. That we explained in the previous slides, that unless you cure properly, you will not get good results. I am going to show you two images which kind of say that it's a real very clear that curing was not done properly. I have been on these sites. So, here we can see this sack is left dry. This sack is very clearly, it is very dry here. It is supposed to be wet, so that you will have this concrete in the near cover or the cover concrete will get enough moisture. But most often what we see on site, construction sites, is that they will only provide this sack, but it will not be wet, especially during the day. So, we must ensure that at least in the initial time of about 2 to 3 weeks, we should have good good amount of water available for the concrete. Like we said, then again we have a shortage of water. So in such cases we should come up with a new technology. One is this curing compounds, where nowadays wax based, resin based and water based curing compounds are available. But there is some concern about this use of curing compound, which people say, okay, there is some issue associated with the efficiency. Anyway, research is still underway. It's not yet picked up much in the Indian construction industry, but this is one way of curing road structures, especially this structure which has large surface to volume ratio. For example, roads. Now in India we are going to construct significant amount of roads. So if all those roads, if you think about making sure that sufficient water is available, there may be some locations where there is significant water shortage. In such cases we can go for this curing compounds. Of course, the strength design for strength has to be taken care by over designing for this loss in the strength if it is done in a moist curing, if the moist curing is practiced. So we can expect some reduction as compared to moist curing. So we have to account for that additional strength requirement. That's the way to go. Now there are different types of durability test available. One is oxygen permeability test, then water permeability test, then water sorptivity test, and then there is a Venner probe resistivity, that is mainly looking at the electrical resistivity, and then there is a rapid chloride penetration test, then there is a accelerated carbonation test. So as you see here, we are looking mainly on oxygen, water, chloride and carbon dioxide, and also electrical resistivity test. So these are the, like oxygen and water, as we mentioned in our part 1, oxygen and water are essential for corrosion to happen, and chloride and carbon dioxide, if there is a presence, it can accelerate the corrosion process. And when we talk about electrical resistivity, it is an essential thing, because if the concrete is having very low resistivity, that means the probability of it's very easy for the corrosion reaction to prolong. If it is highly resistive concrete, then corrosion will be very, very slow. So we'll go through each one of these tests now. And oxygen permeability test, in this what we do is, there is a pressure cylinder. This is the picture of how it looks like. This is a pressure cylinder here, you have a pressure meter here, and in this red is the oxygen cylinder. You supply oxygen from this cylinder to this pressure cylinder here, and there is this small disc of concrete which is placed at the mouth of this pressure cell over here, and then we see how the pressure in the cylinder is dropping. If the concrete is very porous, then there will be the rate of dropping will be very, very fast. So you can actually correlate that drop in the pressure and the quality of the concrete in terms of oxygen permeability. Now there is another one which is a water permeability, where we look at how deep the water can penetrate through the concrete. So here this is the test setup, where you can see a cube is placed here, the 3 specimens you can see, and then this is the pressure water hose which is under pressure. You apply this water, and then you see how deep the water is able to penetrate into the concrete. This is the picture which shows, as you can see here, this is the depth or the region which is through which water could penetrate, and this is a dry region, there is no water. So by comparing different concretes, we can actually check what is the water permeability of the concrete, and then decide on the quality. Another test is water sorptivity test. It measures the rate of sorption of water into the concrete, but this is not really giving a bulk property of the concrete. It captures the near surface property. Of course it has 4 cylinders which is collected from inside, but what when I said near surface, it's basically very near the concrete surface. It's the property which we are looking at is the sorption. Okay, And how do we decide on concrete quality? If the sorptivity is less than 6, then we say it is very good. If it's greater than 15, we say it's very poor. So something like this you can look at. Now, when a 4 probe resistivity test, again here you have 4 probes. As you can see, there is some equipotential line. So what you do is you apply a current between the 2 outer electrodes and measure the potential between the 2 inner electrodes, and then you can calculate the resistivity of the concrete using this current and potential. And then if you get the resistivity and come based on the higher the resistivity, concrete is going to be very good. This is a picture showing the test setup, and this gives a surface property, near surface property. Again, it's a very useful test for field applications where you can very easy to go and measure this thing in the field. And another test is rapid chloride penetration test, where you can see charge passed and how the chloride penetrability is rated. What you do is you take a concrete cylinder and then you try to pass current through this concrete. So on the left side you see a cell, on the right side also you see a cell, and this concrete is sandwiched in between. This is the real picture. This is the one cell for sodium hydroxide and cell for sodium chloride. Here you have concrete cylinder. Then you apply voltage of 60 volt across these two cells. So as you see here, 60 volt is applied, and there is a little mesh here on the surface of the concrete which is in contact with the solution. Now you apply the 60 volt, then what will happen is the chlorides from this end will try to penetrate into the concrete or permeate into the concrete. And you can also check how much charge is being passed. If the charge is very high, electrical charge passed is very high, means greater than 4000, we say the penetrability is very high, means it's very easy for it gives an indication that it's very easy for chlorides to pass through the concrete. So chloride ion penetrability is high, means the quality is poor. So like that you can say as you go down on this table, the quality is going to be better and better. How do we get a visual observation on this? Is you take the cylinder, same cylinder after the RCPT test, you take that cylinder, break it into two pieces, and you can spray on this fresh surface, you spray silver chloride, and you can see that the silver nitrate you spray. When you spray silver nitrate, it will form, if there is chloride present, it will react and form silver chloride. And you can see this white patch here, that is a silver chloride. So it's very clear indication that on this specimen the chloride has penetrated by this depth, this depth chloride penetration. So like this, if you have 2-3 types of concrete available at site, you can actually check what is the quality of that concrete. The higher the depth of chloride penetration, poorer the quality of the concrete. Now how do we can also do chloride test. Here this was a visual observation on how much chloride is there, how much chloride has penetrated. This is a way of getting another very important property called chloride diffusion coefficient, which is an essential parameter for estimating the service life. What we can do is, if you get a real structure, you go and actually this is a profile grinder, you collect concrete powder samples at various depths within the concrete, and then, so as you see here in this picture, this is the depth as you go inside, and then you get the chloride concentration. So near the surface you have higher chloride concentration, as you go into the concrete, the chloride concentration is decreasing. So based on this, we can actually determine what is the diffusion coefficient, which can be later on used for determining the service life. Similarly, in the case of carbonation, what we can do is we make prism specimens of whatever concrete you want to test, put it in this chamber. As you see here, these are the prism specimens which is inside this accelerated carbonation chamber. We can make this concentration of CO2 inside this chamber, maybe we can keep it at 1% or 3% or something in that very high concentration as compared to the ambient or natural carbonation conditions. Then we because of that high concentration of CO2, it will try to penetrate into the concrete at a faster rate than in the case of a natural carbonation. For example, by going by this accelerated carbonation test, we can actually do tests within 3 to 4 months and get a good estimate of how that concrete is going to behave in long term under natural carbonation. So, as you see here, you can see that this near the surface of this concrete specimen, you have no color. Basically, you spray phenolphthalein on this specimen, and then you see near the surface you do not have any color. That indicates that there is a reduction in the pH near the color. So, the reduction in the pH is because of the consumption of calcium hydroxide during the carbonation reaction. So, the more the depth of this colorless region, the more will be the carbonation rate. So, that's the idea and how you use this data to compare different type of concretes. Now, we have seen that enhancing the durability of concrete, there are different ways we can actually use different materials and ensuring that proper proportioning of those materials are done, we can get good quality concrete. And we often see that concrete also cracks, even though we have good best mix design, everything we have seen that concrete can also crack. Ways of controlling the crack is, one is to use some fibers in the concrete. In the previous module, I have shown that one picture where fibers have been used to control the cracking of concrete. Then mineral admixtures can be used, chemical admixtures can be used, but on top of everything, curing is the one of the most important thing. Even if you have the best mix design and all that, unless you cure the concrete properly, you will not get the desired properties. And then one other way of enhancing the durability is going for a good cover thickness. It's not that keep on increasing the cover, then that will have some other structural issues. You will increase the weight of the cover concrete, which is not good. So, optimum cover thickness is what we look for, and ensure that the whatever concrete we have, it is compacted adequately and cured adequately. In general, the quality of construction should be very good, and at the same time regular and preventive maintenance. We should not just leave the concrete structure after the construction. We should ensure that there is regular monitoring of the structure or regular monitoring, and based on whatever the reports which we get, we should go for a preventive maintenance. That should be the approach. It's not the maintenance as a reaction to some deterioration which we see, but the maintenance should be to prevent the deterioration. The remaining section we will take a 10-minute break, and then we will cover the codal provisions which are available, and we will also go through the service life prediction software and preventive maintenance strategies. And I will request you to write down all the questions and queries which you have now. So, this is a corrosion map of India, where you can see along the coastal region you have a very severe corrosive environment, which is kind of what we expect. However, you remember that there are many other locations within the mainland which are far away from the chlorides, from the coastal zone. You can still have corrosion. So, the idea is this map here gives a general corrosion conditions or general exposure conditions, especially looking at the chloride induced corrosion only. Okay, but if you are talking about a map for carbonation induced corrosion, probably the interior area would be much more severe than the coastal region, because carbonation doesn't progress well when you have a high moisture condition or humidity conditions. So you have to go for specific case. If you are talking about chloride induced corrosion, there is a different map. If you are talking about carbonation induced corrosion, you have to consider something separate. And on top of everything, the most important thing is we have to consider the local exposure condition. For example, if you have a chemical plant which is located in this region, for example, and let us say somewhere in the Madhya Pradesh where there is no coastal zone, but for the concrete elements in that chemical plant you can have very significant very severe exposure condition because of the chemical airborne chemicals in the building. So you have to really think about the local climate. That's most important thing. You cannot just say it's far away from the seashore, so my durability conditions would be different. As an engineer, local exposure conditions is most important to be considered. Now, our codes IS 456, it categorizes various exposure conditions into 5 category: mild, moderate, severe, very severe and extreme. This is the table which is given in the IS 456. We will not go more in details into this, but these tables are given in this PowerPoint presentation so that you have a direct reference available. And then next is ACI. They also provide various exposure categories, but mainly looking at the deterioration mechanism, where you can see freezing and thawing, sulfate attack possibility, and where you have carbonation or chloride penetration, then you look at the permeability issues or even moisture conditions, and then in general corrosion protection. So this is different way of categorizing to assess the potential durability of concrete structures and to assess basically the environmental condition so that you can design for durability. Now 456 also gives some clause on what should be the minimum cement content, what should be the maximum cement content, what should be the minimum grade of concrete, and what should be the limits on the chloride and sulfate contents in the cement. That is also included. So this is table 5 in IS 456, where you can see these those 5 exposure conditions which we talked about: mild, moderate, severe, very severe and extreme. And if you are talking about plain concrete, you have these minimum cement content, maximum water cement ratio, and then minimum grade of concrete. And then you have, if you are talking about reinforced concrete, then you have minimum cement content, maximum water cement ratio and the minimum grade of concrete. I will talk one example here. For example, you are in an extreme environmental exposure condition. If you are talking about plain concrete, you must put at least 280 kilogram per meter cube of concrete, and you cannot have more than 0.4 water cement ratio. You have to make sure that your water cement ratio is smaller than this 0.4, and you should design the concrete at least for M25. However, I would say you go for a higher strength concrete if you are talking about reinforced concrete. This table, this portion of the table, it's for plain concrete. There is no steel, so you are not worried about corrosion in this part. If you are talking about reinforced concrete, you have to have a minimum cement content of 360 for the extreme case, and a maximum water cement ratio of 0.4, and grade of concrete must be at least M40. So you go for higher grade of concrete and lower water cement ratio, and minimum cement content is also specified. Also, we should not put more than there should be also a upper limit for the cement content, because over the if you put too much of cement, then it can lead to thermal cracks and shrinkage related issues. And if there is a crack, then it can lead to other deterioration mechanisms as well. So for example, in concrete, when we talked about shrinkage, in concrete the element or the component which is shrinking is the cement paste. The aggregates do not shrink. So if you put more cement in concrete, that means it's going to be shrinking more as compared to a concrete with less cement content. So that conceptually you should understand that. Now durability relation, again the test and standards of acceptance. There is a cube compressive strength is something which we look at, and then we also look at what is the amount of chlorides and sulfates present in the cement. And then in the fresh concrete, if you are talking density of the concrete, that is something which we look at. And in the hardened concrete, we also do permeability tests. These are some of the basics. See, we discussed so many different type of durability tests in the previous slides, but what we see here is not all of them are being implemented yet in Indian codes. So there is again long way, but the codes are being modified as we talk. Codes are being modified so that we can ensure that our future constructed facilities will last longer, the concrete will be of better quality. So this RCPT is the one of the most widely used test method to check the resistance against chloride attack. But of course, as a point I would mention, there are some issues associated with RCPT. You cannot blindly go with the numbers alone. That's why we also do this silver nitrate test to check actually how much chlorides has penetrated, because the coulomb which we measure in RCPT, it is not necessary, it doesn't necessarily represent the chlorides. If there are other negatively charged ions, they will also actually influence those coulomb readings or the charge readings. So we should be a little bit careful when you assess the RCPT test results. Then there is a water permeability test is also used by railways for various projects. And if you are talking about seawater or a coastal exposure where you have a significant amount of sulfates and chlorides present, then we go for a cement with a low C3A content, which is basically sulfate resistant cement. We can also use very high quantity of slag. Even up to 50% replacement of slag is being used in many places. PPC or Portland cement, Portland pozzolana cement can be used at least at M20 grade of plain concrete in the case of reinforced M30. So this depends on which condition, like the table which I mentioned, this table can be used to determine to decide on what should be the cement content, how much water cement ratio and grade of concrete, etc. Now corrosion of rebars, it will depend on the exposure condition, the type of concrete, etc. So we for the same concrete, if you want a higher life, we go for a cover, increase the concrete cover. Either increase the concrete cover or increase the quality of the concrete. Either way we can actually enhance the corrosion resistance of the structure. Now if you are talking about cracking, there is a provision that the crack width at the surface of the concrete should not be more than 0.3 mm, and it's limited to 0.2 mm, and it should not be more than 0.3. Okay, now how do you mitigate sulfate attack? C3A, if you reduce the amount of C3A in concrete to less than 5%, we can really increase the resistance against sulfate attack. And fineness also we can put a minimum limit, means it should not be too fine. And soundness, which is the resistance against cracking, it should not, the volumetric expansion we look at, there's a soundness test available. It should not be more than 0.8%. Setting time, we put a limit, it should set within 30 minutes, or initial setting should happen within 30 minutes. This is mainly to control the quantity of the gypsum actually. Then suggestions is again use low C3A cement, low water cement ratio, use SCMs, and if you go for low water cement ratio, also at the same time you may have to use the chemical admixtures also to ensure that you get good workability. So this is a table for sulfate attack given in ACI 211. Then this is specifications on how to rate the quality of the concrete as a function of surface resistivity, charge passed or RCPT test, and there is another test which I did not discuss earlier, which is non-steady state migration coefficient, and then chloride conductivity. The last two tests I haven't discussed in the previous slides, but it is also widely used, especially not in India but abroad. So we can actually do these tests, and as you see on the screen, there is a condition and or condition. So what we are saying is surface resistivity and RCPT you consider and condition, that these two should be met if the resistivity is greater than 20 and if charge passed is less than 1000, then we can say it. If both these are met, then we can say excellent condition. So these combinations you have to look at. What it essentially means is it's not just the concrete should pass either one of the criteria, you may have to look at combinations to decide whether it is good or bad. Now all these durability tests which we discussed, this is just a summary, what is the test method and what are the parameters which we look at associated with these tests. For example, in the oxygen permeability test, we look at something called oxygen permeability index. So then that index we have a specification. If it is above, I think it is 9.75 above, it's a log scale. So there are different tables available to check whether the concrete is good or bad. The higher the index, the better the quality of the concrete. Now here, this is one way of implementing these durability parameters, or how we can do that so that the contractors actually accept this philosophy and make it in practice. Or we can even do this during the initial contract documents itself. We can say I will accept the concrete only if these particular parameters are being met. And what happens is, normally at site during the early, like before actual construction, you will test the concrete in the laboratory, and in the laboratory you will have very good quality control measures, and then maybe your concrete will pass the requirements. But at the site, how do you ensure that that is being practiced, that those good quality construction practices, I mean, how do you check that, or how do you motivate the actual site personnel to ensure this thing? So this is one way of doing, is put some conditions or acceptance or rejection criteria. For example, here in this slide, what you see is the condition is that in the contract document itself, this is an example from a project in South Africa where they have actually adopted this. The oxygen permeability index, or OPI, what they said is they will measure the oxygen permeability index on the concrete structures after the structure is built. After 28 days, they come back and then check the concrete oxygen permeability index, and if the oxygen permeability index is greater than 9.7, payment, 100% payment will be made. If the oxygen permeability index is between 9.25 and 9.7, then only 85% of the payment will be made. So there is a penalty of 15%. So this is the way to go. So if you have some condition kept on these parameters, so there is a motivation, the workers at site or the engineers at site will be motivated to achieve these target values. And if it is found to be less than this, then not applicable, or there is no payment, that's or you have to either demolish the structure or do something else. At least if you put these kind of conditions in the contract documents, I think definitely we can increase the or enhance the quality of our concrete structures. I will briefly go through the service life prediction. So what is service life? When you say durability of concrete structures, durability, if you want to talk in terms of some numbers, we have to bring in some numbers in terms of life or number of years or time for which the structure will meet its requirements in a safe manner. So what you see on the screen is a schematic of what we call overall service life, means from this point till this point the structure is in use. So this blue region here is the initiation phase. It means corrosion starts right here. From this is the commissioning time. From there, this is the time at which corrosion starts or corrosion initiation time. So this region is corrosion initiation phase, and then the corrosion starts and then it propagates. So this is that phase, corrosion propagation phase, and then there is some more, we will keep on doing some repair on the structure so that we can continue to use the structure. You can see here there are 4 repairs being done on this structure or on this drawing. It indicates 4 repairs, and most of the time what we see is after some couple of cycles of repair, we see that it is actually better to actually rebuild, replace that structure and not to spend any more money on repairing that structure. So this is the end of the life of the structure. Okay, so the 3 phases: initiation phase, propagation phase, and repair phase. And most often the initiation phase is much longer than the propagation phase and the repair phase. If you say initiation phase, how to increase the length of the initiation phase or duration of the initiation phase? How do we do that? Is by increasing the either the quality of the steel or by increasing the quality of the concrete cover. So the initiation phase is typically the longest phase, and determining the duration of this phase is very important in determining a structure's service life. So we should be able to determine when the structure is going to start corroding, that is this point, at the design stage itself or before even choosing the materials for construction. That's a challenge. So there are some tools available to actually do that estimation. One of the widely used tool is software called Life 365. This was made by a consortium of all these companies, and ACI committee actually approved this. So this Life 365, it's a free software available. I request you to download this software and you can actually learn how to do this service life prediction. Now this is a snapshot of the screen. What you can see here is we can try different options, and if you know the diffusion coefficient of the concrete which you use you can enter that. There is also options available to use whichever diffusion coefficient which you want to try, and then the M is the decay factor. So this we have to see for different type of concrete what is the suitable decay factor, and depending on the type of steel there are options: black steel, stainless. Black steel is the conventional steel, stainless steel, and if you have different type of admixtures or mineral admixtures, for example, how much slag you used, how much slag, fly ash, silica, you can enter the mixture proportion details. What it will do is it will actually use these mixture proportion details and some existing information. It will calculate or define its diffusion coefficient. You can also enter your own user defined diffusion coefficient also. Anyway, the idea is, based on all this information, we can actually estimate the initiation time. For example, these curves shows the initiation time, and in probabilistic manner, not in terms of a deterministic manner. So for example, this red curve here, it's this case here, and it says that that structure will have an initiation time of initiation time of about 65 years. Okay, the highest probability or the median value is 65 years. It's not the mean value, but because it's not the standard normal distribution, it's a different log normal distribution which you see. Now this is an example which shows how the water cement ratio, fly ash and silica fume can influence the time to corrosion initiation. Now here in the first 3 rows you can see 0.4 is the water cement ratio, and in the first one you see no fly ash, no silica fume, you get 60 years of life. In the second case you have 0.4 water cement ratio, 15% fly ash and no silica fume, you get a plus 20 years, 20 more years by using 15% fly ash. Instead of fly ash, if you put silica fume 15%, you get 180 years, but we normally don't use 15% silica fume, we use much smaller quantity, let's say less than 5%. But the idea here is to show you that we can really enhance the service life by changing the materials which we use. And also if you compare the row 1 and row 4, you can see that the time to corrosion initiation is decreasing from 60 to 40. That is a reduction in 20 years by when you increase the water cement ratio. So in Bandra Valley Sea Link, they have actually used silica fume concrete to increase the life, because this is right in the ocean, which is rich, very aggressive environment. You have a lot of chlorides here. So you have to have a highly impermeable concrete so that the rebars inside is well protected. Now when you talk about fly ash, there is a lot of concern in the industry, like there is some people do not allow to use fly ash in the concrete even today, even some agencies do not allow. But I just wanted to show you that we it's definitely, we believe that using fly ash is going to enhance the life of the structure. This was a couple of projects which we did it at IIT Madras, and we can see as you use fly ash instead of OPC concrete, you get increase in life. So the maroon color here, these two charts, these two bars indicate increase in the life as with the use of fly ash. So nutshell here is about 30% or more fly ash and appropriate mix design. This is very crucial. Appropriate mix design is very crucial, and I would even add curing also very crucial, could increase the service life by up to 50%. That means you can have significant increase in the durability if you go for using fly ash, slag, silica fume, metakaolin, all these mineral admixtures or SCMs. Okay, one more thing I would like to mention, technology is also available to use fly ash and design concrete structures resistant to carbonation induced corrosion, because there are some concerns among the industry that this might actually use of a lot of mineral admixtures might adversely affect the carbonation induced corrosion. However, there is not much literature available today to really prove that point. So work is ongoing, but in general we can definitely get, because if you look at functionally equivalent concrete, in other words for the similar strength concrete, we can still design concretes with fly ash and slag etc. to resist CO2 induced corrosion for the desired. So the point is, we should know what is the desired life. For that life we can use these materials, fly ash, slag, all these SCMs, and design structures whatever be the corrosion mechanism. So we can definitely use these materials and use appropriate mix design techniques to come up with good concrete designs. Preventive maintenance, I have only one thing to say here. So this is a picture from one of the metropolitan cities in India. What you see here is a lot of trees this growing on this concrete, I mean this structure here, and most of the time, see, you can see here there is an air conditioning unit. It's actually giving an enough moisture for these small plants to grow around, and this is like a feather on top of this chimney. It's actually a tree growing on top of the chimney. See, these kind of things we can definitely avoid if our engineers are knowledgeable and careful about maintaining their structure, whichever structures for which they are responsible for. If they do proper maintenance, we can definitely prevent a lot of deterioration, or at least extend the life of the structure. So preventive maintenance approach is very much essential. We should not allow these things to happen. What is the problem here is, these trees grow here, the roots exert significant expansive stresses, which will lead to cracking and all sorts of problems on these structures. So we should actually go for not just maintenance approach, but a preventive maintenance approach is what we have to adopt. Now towards the end, I would say, what is quality? Quality means doing it right when no one is looking, means we have to feel from within that whatever we do should be, whatever the structures we construct should be of good quality. We should feel for it. That's most important. It's not that somebody just forces you to do things. So you once you start feeling for that, then things will go in better way. And strive for perfection in everything you do. That's a quote by Henry Royce. So, but I believe where there is a will, there is a way. If you really want to get things done, you will find a way to do it. Here what you see is, or I will rather leave it to you. See what he is doing is, with whatever resources available, we should try to do the best way. So here he doesn't have a proper sieve, but he is using his own code to sieve the sand. I am not telling to practice this on site, but try to use all the resources available, both men and materials, and then you make the best out of it. Thank you very much. Now we'll go into the question answer session.
Hello.
Yes, go ahead.
Sir, how is the curing for the precast member is different for the how is the curing for the precast member is different from the normal member of the concrete?
It's not different.
Then, sir, how can we differentiate between them?
Between them means what and what? There is no difference. You should do same type of concrete, same type of curing for precast members also.
Then there must be a difference between the durability in both the cases.
That's what, when you go for precast concrete members, you have mostly better quality control possible, because you are doing it in a controlled environment, unlike in situ concrete. So that is why we expect precast concrete to have better quality. And also when you talk about precast concrete, you will have multiple elements of same size and shape. So as we move on, we learn more about that process. Okay, the workers also learn better. So there is a improvement in the skill level of the worker. So eventually you get better quality concrete.
Okay, sir. Sir, one more question. How can we prevent the sorptivity of the water
The answer to that is, there is no difference in the curing. Both concrete, the curing requirement depends on the type of concrete. Whether it is precast or in situ, concrete doesn't know whether it is in a precast site or in situ, right? So it has to be treated in the same way. Yes, next question.
Sir, how can we prevent the sorptivity of the water into the concrete?
To make it more compact. So this is basically because of the capillary action. So you make, you cure the concrete better, you will use more mineral admixtures, you will get more compact microstructure. So you will not have that much sorption of water.
Only one way, that is by compacting we can do that.
Now when I say by compacting, I am not meaning by vibration and compacting that way. I am meaning by modify the mix design and ensure that complete hydration is happening.
Okay, sir. Thank you, sir.
Yes.
I want to know how the surface curing of the concrete affects the concrete in bulk if the water permeability of the concrete is poor?
When we talk about curing, even if the outer concrete is dry, that outer concrete will protect or prevent evaporation from inside to some extent. So that will protect the, so inner concrete will have enough water to cure. So you might have good strength but not durability. If you don't cure the concrete properly, if you don't cure the surface concrete properly, the structure might have good strength in the beginning, but it will not have good durability.
Sir, I had a query that
Yes.
in mass concreting, sir, there is a lot of heat of hydration, and heat of
Yes.
hydration affects the strength of the concrete. So, sir, how the strength is achieved in mass concreting, sir?
There is a lot of heat of hydration, and then what did you say?
Sir, there's a lot of heat of hydration in mass concreting. Sir, it affects
Yes.
the strength. And sir, how that strength is achieved regarding that heat of hydration?
Are you talking about dam structures or a large column in a bridge? Which one you are talking?
Sir, I am talking about the dam structures.
Yeah, so there most of the time what we do is we use a concrete which is we use cement which is having high concentration of C2S. So even though heat of the total heat of hydration is high, it will happen very slowly. So the rate of heat of hydration is less.
Thank you, sir.
So it does not lead to significant cracking in that case. Okay, but if you use a cement which is high in C3S, then it will not be the case. It will lead to cracking. So we use
C2S.
C2S. Yeah. Okay, next.
Which code we refer for software details, sir?
See, in India at this time we don't have a code. It's in the making right now, but we can use. If you go to South African code, it is available. If anybody is interested, you can email me. I'll send you directions on how to get it.
Okay, sir. Another question. For self-curing compound, how it will make uses in, suppose we are using a RioCure.
Can you start off again? Curing?
If you use a self-cure compound, self-cure 736, it good for curing?
What is self-cure? I don't know about that product.
Okay, sir.
No, can you tell me what it
RioCure,
is?
sir. RioCure. It's a self-cure compound.
Okay.
Sir, it's a product from Australia where they use it for, instead of curing, they can use it as a self-curing compound, where if you compare with your wet curing, in fact, the results are almost the same. In fact, it is from
Okay.
BASF, where they import from
Rio,
Australia.
I
Some of the studies and some of the RioCure 736.
Yeah, that is a
We have done some
BASF.
projects using that RioCure 736. Yeah, and
Okay.
in Australia they are using this. There are many projects where they have done with using this
See,
RioCure, where
when
you can avoid curing totally.
okay, no, you said
Yes, sir.
you get almost similar strength, right?
Of course.
Yeah, but the point is when we check this effectiveness of the curing compound, strength is not the parameter to look at. You have to look at durability parameters, and then if you get similar durability parameters with and without this curing compound, then you can go ahead and use it. Otherwise, what we have seen is even though strength is very good, the durability parameters are not meeting. Moist curing seems to be the best one in that case. So don't look at only the strength. It will not give, it is not sensitive enough to capture the difference between the wet curing and the curing using curing compound. Is that clear?
Yes, sir.
Okay, so not only strength but also other parameters like oxygen permeability is found to be a very good parameter to check the effectiveness of curing compound.
So one more question, sir. So what do you mean by water footprint?
The amount of water which when we go for construction, the amount of water that structure takes to complete the construction. That's what I meant by water footprint. We say carbon footprint, CO2 footprint, all that. But water footprint is something which we in India have to worry about.
Thank you, sir.
Sir, as you said earlier, silica film concrete is long-lasting structure. As the normal concrete compared with silica film concrete, is economical or not?
Of course, you need silica fume. We don't produce it in India. We have to get it from abroad. But the percentage of concrete, percentage of silica fume which we use, it's only 2 to 3%. So very small quantity. But the life you get is much longer. So you have to think whether you are talking about the initial investment cost or capital or the life cycle cost. So if you talk about life cycle cost, it is going to be cheaper.
Okay, thank you, sir.
And when you talk about large structures, life cycle cost is what we have to worry about, not the initial cost, because this is where we fail. Most people, when they compare the cost, they look at the initial cost and then keep on repairing the structure, so that your overall cost is going to be much more than the initial cost. So if you go for a durable option, you can save a lot of money in the long run.
Okay, thank you, sir.
Can you elaborate filler effect?
Elaborate what?
Filler
Filler
effect
effect.
on compressive
Yeah.
strength.
Yes, so if filler effect, what I meant there was, if you have a concrete and if there is any unhydrated cement or mineral admixture grains, it will occupy the space. It will not, if there is not enough, because most of these cases you will not have high water cement ratio. So you will have some cement grains which is unhydrated, and if it is occupying these fine pores within the concrete, it will actually help in giving that compaction which is required, or compactness which is required, but not by binding action, but only by a filling action. When you say binding action, you expect the formation of CSH. When you say filling action, you expect only that material to occupy that space but not bind anything. Is that clear?
Sir, one more, some clarification. Sir, in concrete, we have what is known as a filler effect. No, not clear, sir. One more question I would like to ask. In concrete, we have what is known as a filler effect, where filler is going to. That means to say. 1 minute, sir, please. That means to say, can we use the quantity of filler too much? Any limit for using that, or what will happen if you use a huge quantity?
No, it is not by purpose. It is not designed by. You don't put it as a filler like that. There are some material we put as filler, which is, for example, abroad you use a lot of this limestone, ground limestone powder as an inert filler. Okay, how and when we use that is, for example, if you have, let's say, all these materials you put together and then you find that there are some air voids available, so we use it as a filler. Limestone powder is used as one of the filler, which we don't practice in India much. Okay, so it depends on what materials you have and how to ensure that you get maximum particle packing. That is where the idea of filler effect comes in. Sorption. So it's basically the absorption of water through the fine pores and capillary pores available in the concrete surface. It sucks the water inside, inward. It's not a chemical reaction, it just gets the water into the concrete through the fine pores available. That's what is called sorption. What is OPI? One of the question is, it's written in the slide, oxygen permeability index. Next question is, concrete can gain full strength without curing but avoided evaporation. How to calculate volume of entrapped water in concrete? I think I don't know what. Oh, this is for super plasticizers, right? So we don't really want to get water entrapped. So I don't know if there is a way to calculate the volume, but it reflects in the workability of the concrete. So the poor the workability, you might have more entrapped water. Then how curing compounds reduce water availability? I didn't understand that question. Curing compounds reduce water availability. Where please specify the question a little bit more, more clarity. Write it with more clarity. How pH value reduces in accelerated carbonation test? What is optivity? pH value reduces in accelerated carbonation test because the carbon dioxide penetrates into the concrete. So near the periphery you can see, or near the surface you can see that colorless region when you pour phenolphthalein or spray phenolphthalein onto that. So how is it reduces is because of the carbonation. I already answered what is optivity. Then how to calculate diffusion coefficient, that one of the slide is given where you calculate the amount of chlorides present at various depths, and based on that and then using the fixed law of diffusion we can calculate the diffusion coefficient. Then after using 15% silica fume we get service life 180 years. Then why we use less than 5? Because if you use more silica fume, the concrete will become very sticky and it will be very difficult to work with that concrete unless we use a lot of water. So you have to optimize the mix. So the optimal mix silica fume concentration is about less than 5%. Sometimes even 2% we use. So it's even 5 is very high quantity. What is the best curing method to enhance the best durability? I would say moist curing. If you can provide sufficient water for at least 28 days if you are talking about OPC cement concrete, and if you are talking about PPC or PSC you go for more than 28 days, then you will get very good life. So if any questions you have regarding the durability of concrete, feel free to email me at pillai@iitm.ac.in. I would be more than happy to respond. But please mention that you are actually in this course, and otherwise I would not know who you are, and make sure your name and from which college you are in, so that I can appropriately respond to your queries. Thank you very much.